Hi everyone, welcome to our second press conference today, which is on cities' resilience to climate change. And we have three speakers taking part in this press conference. The first one is Hendrik Wouters, who is a postdoc researcher at the University of Leuven in Belgium. Then we have Francis Pope, who is a lecturer at the University of Birmingham in the UK. And finally, we have Anna Soserova, who is a PhD researcher at Delft University of Technology in the Netherlands. There was a fourth speaker whose name appears in the press kit, who unfortunately had to cancel at the last minute. But I'm sure the three great presentations will make up for that speaker. So I'll just hand over to Hendrik now, and then we'll open the floor for questions at the end of the press conference. Thank you.
Thank you, Barbara, for the introduction. Yes, I'm Hendrik Wouters. I'm a climate scientist at KU Leuven and Ghent University in Belgium. I'm investigating the relation between urbanization and weather extremes under climate change. Particularly, heat waves will become hotter, longer, and will occur more often during under global warming. And one important question that we ask is how will cities, how this will threaten cities in the future, and how we need to be prepared to be resilient against. So heat waves are already affecting, largely affecting our cities already today. There are reports about labor productivity loss, power surges, damage and failure of infrastructure, excessive hospital admissions, and even severe excessive death rates during heat waves. So you have these heat wave-related problems on the one hand, but you also have the urban heat island effect. So if you put a thermometer in inside of one of the city centers, for example, here for Belgium, like for Antwerp, then you will see that temperatures are warmer in the city center than in the rural area, which is the urban heat island effect. And what we also see is that when we are approaching a heat wave, this urban heat island becomes even more intense. So there's a clear interaction between heat waves and urban heat islands. But how do we quantify heat stress under climate change? For that, we look at how much temperature alarm levels are exceeded during heat waves. For example, for Belgium, you have two temperature alarm levels, one for the minimum temperature and one during nighttime, and one for the maximum temperature during daytime. And you count the exceedance of these thresholds of temperature, and this gives you a measure of how much heat stress is perceived for that heat wave day. So we can do this for the whole country, like Belgium, and we look how heat stress will evolve in the future. And we look first in the past period, from 1981 to 2015. And then we see that for the rural areas in Belgium, we have about 2.5 degree exceedances per year on average. Of course, this doesn't seem much, but for some years it will be 0. But for other years, like for the summer of 2003, it can become 10 degree exceedances or even more. This is for the rural areas. If we look for now, for the present day at the urban areas, we see that the heat stress is much higher. And we come up with an average of 16 degree exceedances per year on average. This is now for the present day situation, in which you clearly see the spots of urbanization on this Belgian map. And if we now look into the future, then we see that heat stress becomes very largely exacerbated. And we see like a factor 4 of heat stress towards the future period. And we also see that this increase is twice as large as compared to the rural areas. But still, the rural areas are also affected by increasing heat stress, and in the future they will experience the same heat stress or even more than of the urban hotspots of today. So, of course, this is only one scenario. This is only one situation outcome for future. A lot depends on how much greenhouse gas we emit and how land use, like urbanization, will evolve in the future. So if we take a very extreme scenario in which we increase the amount of greenhouse gas emissions into the atmosphere, and we have the urban proliferation in the future, then heat stress could exceed for cities over 250 degree exceedances per year. So imagine if you have a summer. So for an average summer, you would have a 25-day period for which the heat wave alarm levels are exceeded by 10 degrees. So this puts large risks to the livability of our cities in the future. Of course, if you take a low emission scenario, a low scenario at the bottom of the graph, then in which we decrease our greenhouse gas emissions, then the heat stress would be about the same as of the present day. So, what we need to do is, of course, prepare ourselves to this extreme heat under climate change in cities. So we need to prepare our cities for this increase in heat, but we also need to drastically cut down our greenhouse gas emissions. And actually, our study actually shows that there's a large responsibility for the local stakeholders. So for the cities itself, that need to actually transform the urban areas into compact, green, and healthy cities with a low carbon footprint. And for this to accomplish, we need interdisciplinary research and collaboration to make it possible. Thank you for your attention. So, yeah.
Perfect, thank you very much. So I'm Francis Pope from the University of Birmingham, and I'm heading up a team of atmospheric scientists, of which I'm one of them, plus epidemiologists, again, from the University of Birmingham. And so what we're interested in is the resilience of urban ambulance services under future climate, meteorology and air pollution scenarios. Today I'm just going to talk about the climate and the meteorology side of it. And this is work funded by the Natural Environment Research Council and the Medical Research Council of the UK. So to put this into context, I mean, it's an obvious point, but ambulances are a key part of any country's infrastructure. So they keep both your citizens safe and they keep your visitors to your country safe. And in this study, we're looking in particular in London, so obviously many tourists. So it's not just our citizens we're concerned about. And within England as a whole, the total number of Category A, which is the most serious call-outs for ambulances, is about 3.1 million. That was in 2015. That's the most recent data I have. And the number of total call-outs in this most serious amount is increasing year by year. And this isn't necessarily driven by temperature or climate. This is more driven by usage. So people are using ambulances more and more, and there's certain reasons behind that. More and more mobile phones, it's easier to call an ambulance. It's potentially more difficult to go to your GP in the UK at the moment under austerity, for example. But the cost of ambulances is expensive. It costs about £2 billion per year, of that 2 billion is about 1.5 billion is actually in the ambulance call-outs, the actual running these ambulances. As a previous talk said, climate change mean temperature is increasing. Not drastically so, but it is increasing, but probably more worrisome for ambulance services and then any other emergency services for that matter is your extreme events are increasing as well. So you're going to have more heat waves, you're potentially going to have more cold waves as well, somewhat perversely. And so this study investigates the relationships between ambulance data, both in terms of how quickly the ambulances respond, so their response rate, and what things are they going to be responding to, so what illness categories are they going to be coming out for. So are you going to have more heart attacks, or are you going to have more respiratory attacks, for example, and how this links between meteorology and air pollution. So these are just some example data. Here, so on the bottom, what we have is the temperature time series for the last 10 years in London, last 8 years maybe in London. And then there's a couple of call-out categories. So the top one is the total call-out, category A call-outs in London. And so what we can see is the total call-out is increasing. It's increasing quite dramatically as well. But many of the call-out categories are showing clear seasonality. So an obvious one is the respiratory one, which is the second from the top. And what we can see is when the temperature decreases, or when it gets to winter time at any rate, what we see is a clear spike in the number of call-outs. And then there's some categories as well which show no seeming temperature dependence, something like abdominal pain. So some things aren't affected by the temperature, but many of the categories are affected by temperature. So within the top 10 call-out categories, about 8 or 7 of them have this clear temperature dependence. Okay, so if we can understand this temperature dependence, we can potentially make our ambulance and service much better. So most of the temperature dependence is negative. So if it gets colder, the amount of call-outs goes up. That's not always the case. So in some categories like dizziness and alcohol-related call-outs, as the temperature rises, you actually get more call-outs. So there's going to be some winners and losers as you get warmer. So you might think that by getting warmer, if most of the categories actually mean that you have less call-outs on average, or at least in a percentage way, then it might mean things are getting better. But remember that the overall call-out is also increasing. So so you're going to have more and more call-outs. So this is some data, again, this is top 10 call-outs. And what we can see here, this is for different times of year. So what's the percentage difference for different times of year compared to the average? And so what we have is essentially the summer and winter, and we also have July, which is typically the warmest month in summer in the UK, and December, which is typically the coldest month in the winter in the UK. And then I've also put in a heat wave, which was July 2006, and a cold wave, which was December 2010. And most of the time, the data is as you might expect. So if you have a call-out category where it's temperature, it's dependent on the temperature, especially when the temperature gets cold, you get more call-outs. So if we look at something like respiratory illness, then in the winter it goes up, and in the coldest month it goes up even further, and if you look at the cold wave, then it goes up even further. But it doesn't always follow this. Sometimes at these extremes you actually get more call-outs, even if normally it is to do with cold temperature. So you might have a heat wave, something which is typically related to cold temperatures. In a heat wave, suddenly you've got another effect comes in. And so what this type of data here, what this now allows us to do, is we can start forecasting call-out categories. So this is for respiratory illness. So just to talk you through this, it's a bit complicated. So this is for 4 years worth of data, and essentially what we've done is we've constructed a model which relies on previous data. So we've fed the model previous data. So we've tuned the model to this previous data, and then we've predicted the final year's worth of data. So here we've predicted the 2013 data. And so the actual, what happened in 2013, or it's the end of 2012, 2013, is the green, and our predicted is the red. And what you can see is we actually capture most of the variability pretty well. This is a simple model. We haven't done too much in here. We've just used a few meteorological parameters in there. And you can see what we've done is that we've actually caught most of the variability very well. The only thing we're missing is the peak, and that's because of the flu season, which isn't temperature dependent. That's more related to when people move around the country and share their germs with each other rather than a specific temperature-related event. But we're very hopeful we're capturing most of this variability. We're going to carry on generating more sophisticated models. We'll hopefully bring in the air pollution soon. So we've shown that, especially with respiratory and some cardiac relationships, there's a clear dependence on air pollution. So just to very briefly summarize, so ambulances are an integral part of a country's infrastructure, meteorology and hence climatic effects, ambulance usage and performance. So not only what categories of illness are people call out the ambulance for, but essentially what response rate will the ambulance get there. And then our recommendation is that we need further research to allow ambulance planners to incorporate bespoke weather forecasts into planning systems. Thank you for your time.
Okay, once again, good afternoon, everyone. My name is Anna Solcerova. I am a researcher at the Delft University of Technology. I'm doing my PhD on the topic of how water influences the temperature in cities. And this is one of the topics I was looking at, and the name says, how cool is Uchimizu? So I guess the first question I need to answer is, what's the Uchimizu? It's a Japanese technique that stems to the Edo period, so 17th century Japan. And back then it was a tradition when water was poured around temples or gardens, streets, to settle the dust and also to cool the environment. And nowadays, Japanese authorities are trying to revive this traditional method. There are web pages that suggest the citizens how to Uchimizu. And one of the main things I want to point out is that you should never use tap water for this, because of course water is a scarce resource. So the use of rain harvesting tank is recommended. And well, that's an interesting method. So of course we wanted to know how much you can cool the city with such a method. So that's what we did, and we found out that you can cool quite substantially, mostly of course close to the ground, because that's where you pour the water. And then, but also at the level of 1.5 meters, 2 meters, that's the height of an average person, the cooling is still around up to 2 degrees. How did we measure this? Well, we used some very sophisticated methods such as bucket of water and duct tape and spreading water around. And we accompanied it with a cube that can measure temperature on very high resolution. This method is called distributed temperature sensing, and it uses optical fiber to measure temperature. So this cube was 1 × 1 × 1 meter. And there are 53 levels, horizontal levels, on which we could measure temperature, and more than 35,000 points of measurements. So that's pretty nice, because it gave us very detailed profiles that look like this in time and the horizontal space. So we could really see how the cooling progresses after we poured the water on the ground. And I already revealed what the cooling effect was. It was between, let's say, 2 and 8 degrees. But the nice thing about this method is that it not only cools the air, but it also subtracts the heat from the ground, because the ground cools first. So if you walk on such a ground, you don't feel the heat radiating so much to you. So it also cools in a way of how people perceive temperature. And this is not only strictly Japanese method. It's been used more or less in many countries. Also in the Netherlands, our professor pours the water on his roof in the summer nights because his bedroom is under the roof. So even things like that can cool the indoor temperatures. And so we think this is very interesting method for also from a perspective of citizen participation, because anyone can pour water on the street. The other methods that could cool the city, as my colleague suggested, are making the city greener, building parks, ponds. But for that, you have to have authority. You can, as a common citizen, just build a park. So this is one of the methods that would work. Thank you.
Thank you very much for your interesting presentations. We'll now open the floor for questions. Those here in the room are welcome to ask questions, or those watching remotely can use the web chat feature. Would anyone like to ask any questions? Please say your name and affiliation.
Hello, my name is Jutta Rasel. I'm a freelance writer. My question is for Mr. Hendrik Waters, because you said one important thing is to have a look on how much we reach over those thresholds during daytime and nighttime. And my question is, how do you calculate those thresholds? I assume they're specific for different cities and maybe belong to like the mid data of the last 10 years or something like that?
Yes, indeed. Yeah. So the temperature alarm levels are based on these are national alarm levels, and these are based on the statistics is like the 95th percentile daily temperature for summer periods. Yes, indeed. So it's a calculation of it's based on a statistical method. Yes, indeed. Yeah.
Hi, Mariette Leroux. I'm with Agence France Presse. I have a question based about Uchimizu. I wonder if you can tell us a bit more about where exactly you did this research, over what period of time, how much water did you use per surface area, again, over what period of time, how much water do you need? And even though you said it is rainwater, is this really the best use of water? Aren't there other methods perhaps that would be better at cooling temperature? Thanks.
Okay. So the first question was about the method specifically. So we performed these measurements right next to the university. There is a paved area that we used as a measurement area. And what we did, we picked 3 times 3 meters area, on which we applied first 1 millimeter, meaning 9 liters of water. Second, 2 millimeters, so 18 liters of water. And then we just took a water hose and watered, we simulated rain pretty much. And there are differences also between the amounts of water and how the air reacts to that. Second question was about if this is the best way of using rainwater, right? I don't dare to say if it's the best, or I wouldn't know, or I wouldn't know precisely where to place this method. But true is that this is a very easy way to use rainwater, as I mentioned. Of course, rainwater harvesting tanks are also very nice for if you have green roofs or if you have a garden of your own. That's also a very good use of rainwater, I think. But this seemed to work very nicely. And as I said, it's very variable method. You don't need to apply it on the ground. It also works on the walls or roofs and it cools the surfaces as well as the air. So I like it. That's my conclusion.
Does anyone have any additional questions?
Hello, my name is Antonio Sanchez with the Spanish News Agency. I have also a question for you. Up to which air temperature is this method effective? I mean, I guess that in a city where in summer you got 45 degrees, the amount of water you have to use is so huge that then the whole point is lost because it's not compensated anymore. So are we talking that this technique is good for cities in which range of summer or temperature?
That's a very specific question. We measured, I'm sorry, I forgot that part of the question of your colleague. We measured during a summer day when it was up to 35 degrees of air temperature, and the ground had up to 47 degrees. So those are pretty much first results that our research is new because we measured on such a fine resolution, but you don't need. One of our conclusions is that you don't need actually that much water. It was already the 1 millimeter of water had pretty nice consequences of 1.5 degree cooling on a human height level, and it cooled the ground by I think around 10 degrees. But of course, you're right. It depends on how warm it is and also what's the humidity of the air, because you're also adding humidity by evaporating water. That didn't have such a big impact in Netherlands, but it might in more humid environments. So definitely this needs to be researched further of what are the boundaries of this method and yeah, how effective is it in different situations.
Did you water once a day?
No, we did 6 experiments with different amounts of water and one also in shade. And it's difficult to conclude since we did only one measurement in shade, but that seems to work the best. Also because the ground was a bit colder, so more heating was left for the air. So.
Sorry, a follow-up. And there is any kind of relationship? I mean, how much have you worked out? How much water do you need for a specific ground? 1 liter each, I don't know, 1 square meter or something like this. There is a proportion of
we haven't seen that much difference between 1 and 2 millimeters, so between 1 liter or 2. But we did see a difference when we water it, when we pretended that it's raining. And that the difference wasn't that much in the magnitude, but in the shape of the black one, the last one, has more, the lower levels cool more. There's always like a drop. But the black one with a lot of water, the strong cooling reaches higher. So that's our first impression. But again, that was one measurement, and there are a lot of factors that need to be taken into account. So, but still interesting.
Oliver Lefgren from news agency Wissenschaft Aktuell in Germany. Ms. Sosa-Raba to Oshimusi. What do you suggest to the hot cities in Europe or all over the world? Should they install automatic systems to water some parking places, so on? Or do you suggest for every household to have a can of water there for hot days and to go out every 2 hours and, yeah, do the area and the surrounding to water it?
That's a very interesting question. There is, I don't want to steal my own, to give my thunder to someone else, but there is a research group in Paris that did install sprinklers around some roads in Paris and also Lyon, I think. And so that, and they measured quite nice drop of temperature as well. But of course, one of the things I really like about this method, so that's why I'm giving more personal recommendation than science, is that it's a citizen participation method. And if people in the city are aware of these problems and can participate, that's already also bringing the solution closer to the science closer to people, what we are doing here, and that it's not just difficult numbers, it also works for everyone pretty much. So I would go for the bucket of water in each household.
Yeah, I had one more follow-up question as well to that. How far outside of the moistened area do you see a cooling effect? I'm trying to envision in a practical application how much. I mean, somebody mentioned a parking lot, but for urban areas where people are walking and, you know, downtown cores, how much of an area would you have to water to get a cooling effect adjacently without people sort of walking directly through the water?
That's That's also a very good question, because there is a lot of research, not on this topic, but also on the effect of parks and ponds and how far they reach. And first answer is it depends a lot on the wind, because the cold air is, of course, carried away by the wind. And it depends on how the buildings, how far they are. In a thinner street, probably the effect is trapped more. And but yes, this effect will be carried away. But if we look at the whole city in a general, it will be carried somewhere. So if we do this along the city, the net urban heat island, as Hendrik was talking about, will be lower. So there will be a general impact on the city. So.
Thanks.
Are there any additional questions for our three speakers? Okay, if not, we'll end the press conference here. You are welcome to approach our speakers for interviews. We have interview rooms available next to the press center that you can book. Just come and speak to us at the info desk here at the press center. And I hope to see you all tomorrow at 9 a.m. for another press conference on water hazards, how floods and storms impact us, and how we impact water resources. Enjoy the rest of today. Thank you very much for coming. Thank you very much for your talks. And I'll see you tomorrow.